Welcome back. We're continuing discussing the topic of numerical solution of ordinary differential equations. And in this video, we're going to talk about certain types of equations that arise that may make the methods we've been discussing harder to apply to get a good solution. Specifically, we'll talk about so-called stiff equations, these more difficult equations that we're talking about right here. We'll talk about the solution to address these difficult equations. We'll talk about adaptive time stepping, and we're going to look at how one would code this, and also describe some MATLAB functions that are already existing. So here's an overview of what we've done so far. We've begun by formulating ODEs, understanding what are ODEs, why we want to use them, describe the canonical numerical ODE problem, which is called the initial value problem, and learn the different types of ODEs and so on. We have then begun discussing how to solve ODEs using the basic Euler method. We saw some examples. We talked about error, multivariate version of Euler method, and so on. In the last video, we talked about higher order methods, the basic idea, and a couple of methods we looked at, including the midpoint and more generally Runge-Kutta methods. And here we're going to talk about these issues that may come up for certain types of equations. So here we have an ODE, a relatively simple ODE, which we would like to solve. We're stating that the ODE here is dy dx, and it's given by this equation here. Dy dx is minus 20y, and let's imagine that we would like to solve this within x belonging to the, let's say, 0, 1 interval, which is what we're plotting here, 0 and 1. I'm sorry, 0 and 1 in this x-axis. And we can see we're going to also look at the y range to be, in this case, from minus 3 to 3, which is what we have here. So if we go ahead and for every single point in this domain that we have written here, we can plot this slope, right, which is essentially dy dx. So if we go to this point here, we evaluate this point, right? Let's say we're going to this point, right? So this is going to be x equals 0.2 and y equals 1. So this is going to be minus 20, and right, so the slope is minus 20, and that's what you get. So you repeat this process for every single possible point in this map, and you get all of these arrows, right? And let's look at some specific initial value problem here. Let's say the following initial value problem, where we have our initial point will be y1. Okay, so we're starting, let's make it a blue mark here. We're starting around here, right? This is our initial point. This is y of 0. So that's given, that's stated at the beginning of the problem. And then we need to solve for y of x for x belonging to 0, 1. That's our task. That's our job now. And let's use Euler's method and let's specifically use this h to be 0.1 in this case. Okay, so here we are. Let's plot the solution. Let's do it in blue. So remember, Euler's method starts, we have to get the slope. The slope is given to us from here, right? And so this is the slope. So I'll draw a line that aligns with this, the slope, right? So, and we will land more or less, roughly speaking, right? We have to go 0.1, so this is where we'll land. So this will be our next point, right? That's one iteration of Euler's method. Let's do once more. We have to repeat the process here. Now we look at the slope, and this is the slope, so I'm going to go, and I have to go up to when this crosses 0.2, right? So I'll say it's roughly speaking, if I have to really align this very carefully, it will be right here, more or less, right? Of course, we're just eyeballing this, so it's not going to be too precise. And let's repeat this process once more. We go to our slope that we identified here. Oops, that's not what I meant to do. And we look at the slope, and we have to go to see until this crosses 0.3, and this will be more or less right here. Let's just do one more, just to drive the point home. We repeat this, and we go to 0.4, and we end up right here. And as you can see, this doesn't look like a great solution. First of all, we haven't described what the solution would be here, but you can see the points are bouncing around, up and down, up and down, up and down. And in fact, you know, we're not converging. Of course, we know what the solution here would be, right? Because this is one of those exponential decay solutions. So if we were to plot the actual solution here, it would be more like this green line that I'm drawing here, right? Which is our exponential decay solution. So in this case, we're lucky we know this answer. But you can see that our numerical solution, computed using Euler's method with a large step size, did not do a good job here, right? So that's the point of the topic, right? Of the topic of this video. So of course, we can get the solution in this case by greatly decreasing the step size. So instead of using 0.1, maybe I'll use 0.01, right? In this case, I'll start here. I'll just take a tiny little step, and I'll do it again, tiny little step, and I'll be much more inclined to follow this particular line here. My solution will be much more accurate, right? So the whole point is we have to use small time steps. Of course, we're using time here, but really the variable is x, so I should have, you know, I could have written small spatial steps, but it's small steps in the independent variable. This leads to a stable solution, to an accurate solution, and stable in the sense that it doesn't have the oscillations that we just described, but it's computationally expensive. Because now we have to compute many more iterations of the method to get the solution between 0 and 1, right? And may also be wasteful, because there may be some sweet spot for some time steps, at least for some kinds of functions, where I can get a solution that is, for practical purposes, just as good as the actual solution, but for a larger time step, right? So some functions, some ODEs may require small time steps, some may not require a time step. So let's look a little bit more closely to the situation when time steps or spatial steps or independent variable steps are important. And this is the so-called it's when the ODEs are known to vary the slope kind of in a fast way, right? So for example, let's look at this ODE here, right? If we do the plot of the slope just in the same picture that we had before, we can see that in this region here, this is somewhat relatively stable, right? It's relatively smooth. The change in slope between this one and this one and this one and this one and so on, the slopes are changing kind of slowly, right? Except for this region, right? When we have x around 2, where we have sort of this Gaussian function here being put in the derivative. So if we were to use some kind of time steps, right, or spatial steps, we may be able to do well with relatively large time steps here and still trace the solution somewhat accurately, right? But then here, if we don't take the correct time step, right, so maybe this one will go way out here, right, and then maybe we go back down, right? So that could be sort of a desirable solution, right? But let's say now let me pretend that I'm going to take some larger time steps, right? So here we may still do relatively okay, right? But then we may completely, if we continue this large time step, and we may completely miss this guy, right? So here's the idea that if the time step is too big, that may not be appropriate for some regions of the function. So how about if we come up with a method, and these equations that tend to do this have this high oscillations in the derivative localized to some particular subregion, subdomain of our independent variable. These are known as stiff ODEs. So what can we do about it? Well, we can change the time step on the fly as we're solving for these equations. And the whole idea basically is that in this region here, we may do well with a large time step, but as soon as we get to here, then we may have to use a much smaller time step to get the actual solution, right? And this plot here sort of shows you that, for example, here if we use the Runge-Kutta method that we just talked about before, with time step 1, right? You go from here to here to here to here and to here to here, and you can see that's much different than if we use time step of 0.06, right? Which is this one that you're seeing. And this time step 0.06 is a much better solution, much more representative of the actual solution we have, and we have this initial value problem here now to be 0.5, right? So we start here. But we didn't need to spend all this time computing all these values here, because you can see that this function with this big time step is roughly speaking the same as the small one. So we wasted a lot of time here, whereas we could have spent, to get an even more accurate solution for the same cost, we could have increased the time step here and decreased where it really mattered, and then increased over here again, right? So that's the whole goal of the method that we're going to talk about. So here is the basic idea about how we can perform adaptive time stepping. And this is a concept that is, we're going to talk in the context of this general Runge-Kutta methods, right? Which we can view the simple Euler methods to be a very basic Runge-Kutta method. So it's a general method, right? So the idea is to compute two solutions of these equations at the same time, right? So let's say we have here our axis, and so here's the independent and here's the dependent variable, and let's say we are going to look at 3 time steps here. So let's say we have our initial value problem, we start here, and let's say for the time being that the slope given at that point was that. So we can compute the solution with one step, one full step, right? This is what this is saying here, right? So use h, for example. So if we use h in this case, we follow along the slope, and let's say this is h here. So our solution in this case would be, well, let's say that here, between here and here is h, right? So this is h, and let's say between here and here it's h over 2. If we take a full step size h, we'll end up more or less here. But now also we'll take two steps, two other steps, meaning I'll also compute the solution at h, and let's say at h over 2, and I'll recompute the derivative here, and let's say this, for some reason it tells me to go over there instead. So if I use half this time step using the same method, I'll end up here instead of here, right? And so in this case, this would be my y1 using a full time step, and I use two half step, right? So it's effectively using step at h over 2 and at h, right? So I computed two numbers here. The first number using a full time step, sort of being lazy, I didn't want to compute too much, I just took a large time step. And this other one, I took two smaller steps to get there. And I can see, and then I can check, are these two numbers the same or close to each other, right? So here we have an error. So we call this the delta, right, or the absolute value of the delta. And we can check, is this delta greater than some threshold, some tolerance value? We call this TOL for tolerance. If this is true, we take a smaller time step. Right? If this value is too big for our purposes, that means that there's a big difference between taking two small time steps and one large time step. So the original time step h that I had may be too big because it will cause some kind of large error, right? On the other hand, we may have the converse situation, where, let's say, we're again starting from, let's say, from this point, and once again we have h over here, right, and this is h over 2, and let's say our solution initially was pointing over here, right? So we take one full time step and we end up over here with that time step. Let's call this y1. But let's say if we did this with two time steps instead, we came here first, and then the slope was slightly different, but not too much, right? Maybe a little bit more up, and then our y2, we ended up here. Right? And in this case, let's say this delta value here was smaller than or equal to some predefined tolerance that we decided. Then we say, well, you know, we don't need to worry too much in this case here, because whether I take a big time step or a small time step, it doesn't really matter that much, because the errors are not, there's not that big a difference. So maybe I can even afford to take a bigger time step. Now, how big and how small, there are many ways to do this, and we're not going to get into this in these videos. But for example, you could increase the time steps by 2, or you can decrease the time steps by half if you decide to do so. There are fancier strategies that are provide a more smooth transition, but here is the pseudocode of what this would look like if you try to do this, right? So you start with, if you try to code this, you start with your initial time, and you solve for the time variable up until some final time that you decide, right? In this case, we decided that the final time was between, let's say, 0 and time 4. Of course, we use the variable x here and not time, but we are just speaking generically. So we start by taking one full step h here, right? And we compute y1, and we predict half there by a step of h over 2, and predict y2 by a step h over 2 from that y half again, right? And then we compute this delta, this truncation error, or the error between using 2 small time steps and 1 big time step. And now, if this error, right, which later on when we use, when you may be using solving for a vector value function, so if you take the absolute value, if it's just one value, but if you're using a vector or system of ODEs, you may have, several variables, and so you may need to take the norm of this vector. But if the absolute value or the norm of the vector is lower than some tolerance, then you take your new y at that larger time step, meaning the h, to be the correct one. You still did 2 time steps, and that's still better than the other one, so you use the right value, but you still advance by h, right? But then you may say, hey, maybe we had too small a time step before. Maybe next iteration I'll multiply by h by 2, right? This 2 here doesn't have to be 2, it can be more conservative than that, but in this code we just did that. On the other hand, if the error is bigger than the tolerance, then maybe I want to use a smaller time step, right? And of course you output from this code your vector containing time variables and y, right? So this is the pseudocode, or hand waving code, or this is essentially a plan for coding an adaptive time step. Now MATLAB has functions that does this already, right? And it actually, you don't have to. There are several ways to adapt the time step. The procedure that MATLAB uses in this ODE 4.5 is not quite what I just described. Is something in the same spirit, right? And there are some functions. So this is the ODE 4.5 that uses this adaptive time stepping. There are some certain functions specially built with consideration for step problems, and this is one of them, for example. Right, and but all of these functions work more or less on the same syntax, right? Whenever there are 2 numbers here for the different orders, for example, and you're passing the function, you're passing the value of the interval that you would like to solve, and the initial value for the initial value problem, and this is the output, which gives you the independent and the dependent variables for the problem.